an article on extreme events and living reviews in solar physics, and the collaborators are Carl Schreiber, Kazunari Shibata, and Ilya Usaska. So this is what I'll cover this morning. Begin with a brief historical overview of research on extreme events, and then discuss worst case scenarios for solar flares and coronal mass ejections. And we'll also cover low latitude aurora, geomagnetic storms, radio bursts, asymmetric radio bursts that can be extreme, super flares on solar type and sun-like stars. There's a difference. And then I talk about solar energetic proton events, and when you see them in space, the acronym is SEP, and those refer to the particles that you see at 1 AU. And then talk about the evolution of thinking on acceleration, proton acceleration at the sun, and then get into the cosmogenic nuclide events. And the last topic is relatively new, and that's it's for some new work on magnetic suppression of coronal mass ejections. Okay, research on extreme events really began with the Carrington event, the flare observed on the sun by Carrington and Hodgson on 1 September 1859. And Carrington's sketch is seen in the upper left-hand corner there. And it shows the active region, and the arrows point to the places where you initially saw the white light emission and its final location indicated by the smaller arrows. Directly below that is an early photograph of the sun. It's a blow-up of that active region. This was taken the day before the flare on the 31st of August. And beyond its historical significance as the first reported solar flare and the first recognized solar terrestrial event, what's remarkable about the Carrington event, the flare in the storm, is that after 160 years, it appears to be have been the perhaps the largest, arguably the largest event that we've ever seen in both of those categories. For the flare, of course, no soft X-ray observations at the time, but from the white light emission and from sudden ionospheric disturbances, we can infer a flare soft X-ray class of X45, which makes it larger than anything we've observed in modern times. Its transit time from the sun to the Earth for the CME was 17.1 hours, and that's only been bettered by an event in August 1972 that took 14.6 hours. And in terms of storm intensity, it ranks in the top 3 with storms in other storms in 1872 and 1921. Now, the citation histogram on the right is a good gauge of the growth of interest in extreme events in particular and space weather in general during the last 2 decades. And that spike there in 2006 is interesting because that was the result of a conference in 2003, the publication of the conference proceedings for a conference in 2003. And just to give some general context of what's going on during the last 2 decades, there was a lot of institutional development in the area of space weather. For example, the Space Weather Journal was first published in 2003. In 2004 saw the start of 2 important series of meetings, the Space Climate Symposium, and also that was the year of the first European Space Weather Week. 2011 saw the first volume of Space Weather and Space Climate. In 2012, the first reviews of extreme events by Riley et al. And Schreiber et al. 2012 also very important scientifically because it saw the first report of a cosmogenic nuclide-based SEP event in 774 AD by Miyake et al. And that same year, Mehera et al. Reported the first super flares on sun-like stars with Kepler observations. And a super flare is a flare that has a radiative energy of greater than 10 to the 33 ergs. And finally, 2017 was the first of a series of paper by Hayakawa and collaborators on historical aurora, which are a window to extreme or great magnetic storms in the past. So for the extreme events, we want to know what's the worst that the sun can do to us. So the worst case scenario because of the impact on our technological infrastructure. And all such studies begin with the largest group that's been observed on the sun since records were started to be kept for this in 1874. And the largest group since then was this spot group that crossed the sun in April 1947. And it had a peak area of over 6,000 millionths of a solar hemisphere. Now, if you have the area of the group, from that you can infer the total on-sign flux in the active region, and from that you can infer the reconnection flux by overlaying a magnetogram with an H-alpha filtergram to see what parts of the magnetic field spot group were affected. And if you do that, you can infer a total reconnection flux for the group in April 1947, and you can put that on the plot on the right from Chernitz et al. Correlation plot between total reconnection flux and Gosok X-ray class, and you would infer a X-ray class of X180 with big uncertainties. It could go anywhere from X80 to X480, and you can also infer a radiative energy for that event of 1.4 times 10 to the 33 ergs, which would be a super flare. Then you can compare that with what's been observed. So you have an 1859 event. You also have an event on 4 November 2003, where you have direct X-ray observations. Unfortunately, it was saturated, but from that and ionospheric disturbances, you can infer a class of about X35. But this was directly observed by the source satellites, so we have a measure of its bolometric energy, and you can see that was within a factor of 3 of that inferred for the April 47 region. Now on to coronal mass ejections. The plot on the left is a CME that was observed during the Halloween sequence in 2003 of great events. And so if you look at you can see the disk of the sun in the center, and that's an EUB, then the occulting disk around that, and then beyond that, coronal mass ejection, and goes all the way around the sun, so it's called a halo CME. On the right is a nice figure from Gopal Swami et al. That shows the distribution of CMEs with a number greater than a given speed. And what Gopal's done in this he's plotted the mean energies for various types of events. So for all CMEs, the average speed is about 400 kilometers per second. And then you go increasingly to higher energies for the higher speeds for these various phenomena that are listed. So the next is metric type 2 bursts. Then you can go down to GM, that's for geomagnetic storms of a given size. And then you go to DH type 2 bursts, which are type 2 bursts that can survive into the interplanetary medium. So it's near decametric, hectometric. And then further on are SEP events. Those are particle events, proton events observed in space for the NOAA criterion of 10 proton flux units greater than at an energy greater than 10 MeV. And then the phenomena that's associated with the fastest CMEs are high energy proton events, ground level events observed by neutron monitors. And those events have an average, the associated CMEs have an average speed of about 2,000 kilometers per second. So to get the energy of the CME to go with the flare estimate for the April 1947 active region, we use an energy apportionment from Imsley et al. And at the bottom, the bar at the bottom is the free magnetic energy. That's the energy available to be released in a flare. And main sinks of that energy are CME kinetic energy and bolometric energy, and they're in a ratio of about 3 to 1 CMEs to flares. And because of projection effects of the observations of CMEs, probably both CME speed and mass are underestimated. So we'll use a ratio of 6 to 1 instead of 3 to 1. And from that, 6 times 1.4 times 10 to the 33, you get CME inferred CME energy of 8.4 times 10 to the 33 ergs. Now, the most energetic CME that's been observed on the sun was on 9 September 2005. It had an energy of 4.2 times 10 to the 33 and a mass of 1.6 times 10 to the 17 grams. So we'll use that mass along with the 8.4 times 10 to the 33 ergs, and we'll infer a CME speed for April 47 worst case scenario of 4,100 kilometers per second. And that's 700 kilometers faster than the fastest observed CME. Okay, as I said, aurora can be a good indicator, low latitude aurora, a good indicator of the intensity of a geomagnetic storm. And the figure on the left it just shows a drawing made in Japan for an aurora in 1770. But these observations are very valuable. What you want to see in an observation is, first of all, you want to know the location of the observer. You also want to know the timing for 2 reasons. One, you want to make sure it was during the nighttime, and also for comparison with other nearby observers. And then if you have the elevation of the aurora above the horizon as you look toward the poles, from that you can get the magnetic latitude of overhead aurora. And the figure on the right, the map on the right, it just shows each of those symbols there is a place where the aurora observed. And so you can see that these historical records can be quite plentiful. So the figure here shows a plot of the lowest magnetic latitude at which aurora is seen overhead, and versus the storm minimum DST. Now the DST and the DST index measures the decrease in the horizontal component of the magnetic field. So the more negative the value, the hourly value of DST, the greater the storm. And the open circles there are a continuation of a plot that's based on smaller storms with values to the left of a minus 400 nanotesla. So these are just the big storms that are plotted. And you can see that the ones with the largest intensity, minimum intensity of about minus 1,000 nanotesla are for those 3 storms I mentioned earlier. It says 1859S because there was, and that stands for 1859 September, because there was a storm that was quite large also that in a few days before that, and that's also plotted in that figure. So again, the 3 most intense storms shown at the bottom, and they all had a lowest latitude of overhead aurora about 25 degrees. Okay, solar radio bursts are a thing that's not often considered in extreme event studies, but we did include it in our review, and turns out that you can have very strong radio bursts in a decimetric range, a fairly narrow range from 1 to 1.5 gigahertz. And the best of my knowledge, these are the strongest fluxes that are seen anywhere in the solar radio spectrum. They can go up to a million degrees, a million solar flux units. And examples of 3 of those events are shown in the time profiles of 3 different events. And then direct your attention to the plot on the left for the event on 14 December 2006. Now, in each of these panels, multiple frequencies are plotted, and in each case, the red or the red-orange on the rightmost panel is the decimetric emission. So for that 14 December 2006 event, there's a dashed black line there, and that's the soft X-ray emission. And you can see for this event that at the impulsive phase of the flare early on, all of the frequencies are pretty close to each other with a peak intensity of about 1,000 flux units. And then they stay together for a while until they diverge, and the divergence is all on the part of the decimetric emission. So it rises above the other traces and its own trace and goes along for some tens of minutes, and then abruptly drops back to where it was before with the other frequencies as if nothing had happened. And the interpretation of this is that underlying emission is attributed to a incoherent gyrosynchrotron mechanism. That's why they accept it. And the decimetric emission, the enhanced decimetric emission, is attributed to a coherent process. It gives you spike emission, and you can get these very high peak intensities. And it's a result of an instability, and the emission mechanism would either be electron cyclotron maser emission or plasma emission. And because of their association with CMEs, these are also these events that occur in the post-eruptive phase of flares. I used to call it post-flare loop phase. And they're very large intensities. They would seem to be good candidates to look for mass ejections on stars. This type of extreme event has its own name. It's called a dragon king. It's a dragon because of its unusual nature, and king because it's large. And it can involve amplifying mechanisms not fully active for the rest of the population. And that's what we see with the coherent radio emission. Okay, so now on to super flares on solar type stars. So the first report of these were made by Meher in 2012, and this work has been pioneered by the group at Kyoto University. And now by a solar type star, it's a G-type main sequence. It can have similar effective temperature and gravity, but what makes it not a sun-like star is its rotation period, which are in a range from 10 to 17 days for the ones that have been observed versus 25 days for the sun. And as a result of that faster rotation period, you get winds up larger sunspots, and you can see that in the artist's conception on the right there of a star with great spot groups on it. Because of those large spot groups, you can see very easily determine the rotation period photometrically. That's shown on the plot in the bottom there. And there's an inset showing super flare off to the right of that plot. And this brightness variation can be anywhere from 0.1% to 1%, as shown in the figure. And that's huge compared to what it would be for the sun, because at the sun, the variation from maximum to minimum in the solar cycle is only 0.1%. These large groups, spot groups, can produce flares with energy up to 3 times 10 to the 34 ergs, which is twice what is 2 orders of magnitude more than has been directly observed for the sun, and an order of magnitude more than what might have been produced for the sun in the 774 AD STEP event. So these are solar type stars. So difference for a sun-like star, it has the same temperature range, gravity, and so on. But here the rotation period is 25 days. And the status on that is said very succinctly by Okamoto in the most recent study paper from the Kyoto group. And it says the number of sun-like superflare stars that have been investigated spectroscopically and confirmed to be single sun-like stars is now 0. So that's where we stand after a decade of searching. And that's due in part to this near balance of faculae and spots on the sun, bright areas and dark areas that make it difficult to determine the rotation period. The sun is a star. It's doubtful that we could get a rotation period from it. So even if it was producing superflares, we wouldn't be able to identify it as a sun-like star. And beyond that, while the Kepler and TESS observations are readily available, they need to be confirmed spectroscopically to rule out binarity and also to confirm the rotation period Dopplership. And but we can say that while there's no direct evidence that a sun-like star has produced a superflare, we have this evidence that the sun may have done just that. Okay, the thinking on proton acceleration on the sun of the steps, the particles that observed at Earth has changed dramatically during the time that I've been in this field. That doesn't mean it's been a quick change. When the Forbush discovered the first proton event for the ionization chamber in 1946, all we had was the solar flares, and so they were the default choice for the acceleration of proton events. And the picture was that acceleration of these protons was a delta function in space and time. The delta function in both cases being the flare, localized process for a limited amount of time. And the current picture is quite different from that. Now we believe that the principal mechanism for large, high energy solar proton events are CME-driven shocks. And they can accelerate particles over a wide range of solar longitudes and for an extended period of time. The first inkling of this mechanism was provided by a trio of Australian radio astronomers, Wildsford and Weiss, in an annual reviews paper in 1963. And in their picture, they looked at fast drift type 3 burst that was seen at the impulsive phase of flares and correctly identified that with electron acceleration. At the time, they didn't think any protons were accelerated in the flare. And in fact, in order to get those protons that you observe at Earth, you needed a shock wave that they associated with a metric type 2 burst. And observational evidence for this picture was provided by Lin from early spacecraft observations in 1970. Killer et al. In 1978 added the CMEs to the picture, and designed Giacalone in the review paper is the first place I think I've seen a full-throated endorsement of this picture for large energetic particle events. So it's taken that long. It's really only within the last decade, I think, that this is accepted. But as with all things at the sun, it's not accepted by everyone. That's good because it sharpens the arguments and helps things to progress. Now, there are the principal reason, so this debate continues, this flare versus shock debate continues at high energies. The principal reason for thinking that you could get high energy particles out of a flare is that it's observed. It's observed by, it's first observed by SMM and more recently by Fermilab, that you can see evidence of acceleration of protons to 300 MeV that you need to produce create pions. And so the figure there is this is the standard cartoon for an eruptive flare at the sun, and it occurs because you have a loop that rises up, and as it goes into the corona, it gets pinched off by pressure balance, and it creates an X type reconnection point, and that releases energy, and particles can be accelerated there by various mechanisms, directed electric field, some kind of stochastic process. But those particles that are accelerated either can go down and end up in the pinched off loops, or they can go up and and end up in the structure of the CME. Now, the other place that the protons can be accelerated is the rising CME will drive a shock, a quasi-parallel shock, because the shock motion is parallel to the magnetic field. And the lateral expansion of the C can give rise to a perpendicular shock. And shock mechanism has the great advantage for SEPs that the acceleration takes place on open field lines. So you don't have any problems of getting the particles don't need to escape from some kind of a trap. It might be the case for the particles that accelerated in a flare. And there's more direct evidence for that, for acceleration of high energy particles at shocks beyond the ones that you observe at Earth. And that goes back to a paper by Vestren and Forrest in 1993 for a large particle event on 29 September 1989, where there was a region within at West 100. And what they saw 2.2 MeV gamma ray emission for this in a fairly strong source, and that's not expected because you have limb darkening for this type of emission. And so from that, they infer that the particles must have been hitting the sun on the front side of the disk, where you can see the emission directly, where it wouldn't be occulted, and it could extend 30 degrees from the flare side toward the front side of the disk. And so at the time, we made a cartoon for this, and the picture we had was that, okay, so the CME is at West 100, slightly behind the limb. It drives a shock wave. That shock wave wraps around and intercepts the field line that's connected, magnetic field line that's connected to Earth, and accelerates particles there, and they can travel to Earth as SEPs. And this was the general picture at the time, that the widespread propagation could be due to a widespread shock. But then we suggested that particles could also travel inward from the shock and precipitate in the sun and give rise to gamma ray emission to account for this observation from Vestren and Forrest. And so then you can actually see there's evidence for acceleration of these particles, both at the sun through interacting particles and in space from particles observed at Earth. And not a lot happened on this field from the time we wrote this paper until the Fermi lab began to see more events beyond the sun, and that sparked a wide range of interest in these spatially extended and also temporally extended gamma ray events. And the consensus is most of these are in favor of this kind of picture, but there's not complete agreement. Okay, now let's take a look at the cosmogenic nuclide event in 774. So on the left panel, you have carbon-14 concentration, annual concentrations from 2 tree rings at the time of the 774 event. And when you look at this, it looks like a typical proton event, fast rise and gradual decay, but then you realize that the time scale is 1,000 times longer. And that's because once the particles are created and precipitate out, they have to go through this complex carbon cycle which can have them showing up in tree rings from given event decades later. The right-hand panel gives the ratio of the carbon production, the annual carbon production for the cosmogenic nuclide events that have been identified so far. And the first 5 there are confirmed events. There's 3 under a question mark. They need to be confirmed. The event on the right is the event against which the ratio is taken. That's the ground level event on 23 February 1956, and that shows the carbon-14 concentration that you might expect from it. And the dashed red line is the sensitivity of the method, and so this event would not have been detected. But remarkable thing is that the ratio for the 774 event to that event is a factor of 70. And what does that mean for a flare size? Does that imply a flare that's 70 times stronger? So to get to that, the first thing we do is we take a correlation plot of the log of the 200 MeV fluence versus the log of the soft X-ray flux, and we do that for a sample of ground level events from 1976 to 2012. Western Hemisphere to remove propagation events, effects, hard spectrum like the 774 event, and we make a power law fit to that, the solid line. And we'd like to use the 1956 event, what was the largest ground level event observed in modern times, twice as large as the next largest event, and use that as a bridge to the 774 event. We don't know its soft X-ray emission. Again, no soft X-ray observations in 1956, but we do the same thing that we did for the Carrington event and make inferences based on sun ionospheric disturbances. More observations available for this event, for example, radio burst. And we get a soft X-ray range from X10 to X30. The blue points, then we put dashed lines through them parallel to the solid line and extrapolate up to the fluence of the 774 event, get a soft X-ray range from X145 to 425, take the arithmetic mean 285, and you get a bolometric energy of about 2 times 10 to the 33 ergs. Again, this would be a super flare. So we check that against the upper limit there. 425 is within our upper estimate of X480 for the April 1947 active region. Another consideration is the poor time resolution of the cosmogenic nuclide events. In 3 rings, 1 year. With beryllium-10, you can get several months, but on the sun, we know that you can get 3 typical large events within a week. And so this the 774 event could be due to several eruptions that combine to give you a single step event. And so we just take the case of 2 equal size step events, and then that would imply 2 X180 flares, which just by coincidence happens to be the nominal value for the worst case based on April 1947. Why was this event so strong? Well, it's various speculations on this. One interesting study, interesting work done by Kong et al. Normally, when we think of shock acceleration, we are looking principally at the shock itself. How fast was it? But they point out that there's another consideration. What was the magnetic field like at the foot point of the magnetic spiral to Earth? You can think of that as the target. And they made 2 cases, one where you have a magnetic streamer there, and another where you just have kind of ambient radial field. It makes a big difference. The solid lines there show that at high energies you get orders of magnitude enhancement over the case where you just have radial field. 2 different colors are just different heights in the corona. So we looked at 1956 event and we see something like that. This was a couple of days before the flare. This was the 21st of February. The flare was on the 23rd, but there, that oval shows that there are kind of north-south oriented filaments lying at the right location to put it at the nominal west 50, west 60 reconnection point a couple of days later. And you can see where the flare originated off to the side in an active region. So the cartoon for that is that an eruptive flare, the dashed lines indicate that it's moving outward. It accelerates the shock, it propagates off, and then strikes the streamer. So this is one possible explanation for how a step event could get so big compared to what we've seen during the recent period, which had very strong solar activity. Okay, let's see for time. Okay. A few minutes left. Okay, this is a probability, occurrence probability distribution function for 200 MeV protons, and a couple of things that are interesting about this. One is that there seems to be a fairly good connection between the events on the left, all of the triangles, those are space age observations, and the events on the right, the circles and the stars on the right, which are the cosmogenic nuclide events. All looks like a very good fit. It is a little disturbing or a little troubling that there's this big gap there. Now, part of that is due to the limited sensitivity for the cosmogenic nuclide events. But I think for corroboration of the SEP hypothesis for these large events, what we'd like to see, maybe it wouldn't be good from a space weather aspect, but it would be nice to see an event about 3 times larger than the 1956 event I think that would go a long way towards supporting that hypothesis. Okay, last topic, evidence of suppression of coronal mass ejections on the sun and active stars. This is quite, was first pointed out that you could have strong flares without coronal mass ejections about 20 years ago, and a lot of research done on it since. But the key event was the observation of a large spot group in October of 2014, which was very flare prolific. It had 6 X-class soft X-ray flares and numerous M-class, and very little evidence for associated coronal mass ejections. So this is something we wanted to look into, and so I did with Werner Potzi and Astrid Veronik, and we looked at the relationship of large sunspot groups and great magnetic storms. So the first thing to do is to make a table of great magnetic storms from 1932 to 2014. These aren't extreme events, but they are hefty with minimum DST values less than -300 nanotesla. And there were 30 such events. So then the next thing was to look at the spot groups, the other side of the equation. And here we made a list of the 7 largest spot groups since records were started being kept in 1874. And remarkably, 5 of them, so the 5 largest spot groups, all came from the same active region, from the same solar cycle, cycle 18 from 1944 to 1954. The 6th largest is the group in October 2014. The 7th largest was a large region in March of '89 that produced the largest magnetic storm in the modern era with a minimum intensity of -600 nanotesla. So the panels below that show the DST, hourly DST index for the months of some of these active regions. So the first one is for the large spot group in May of 1951, the largest on the list above. And you can see the arrows give the time of the disk passage of the region across the sun. You can see that very little activity there, and certainly no decreases down to 300 or 200 or even 100. And this was remarked on at the time that they realized at the time this was unusual. And of course, this is pre-CMEs, and so but it caught their attention. And then below that is October 2014. You can see very similar during this passage, nothing. The most geomagnetically, just for contrast, the geomagnetically most active month was in September of 1957, where we had 3 of these great storms, and another one that was got into the 200 range, and the largest spot group on any day during that month was only 2,000, about 2,000 millions of solar hemisphere. So almost done. Okay, on the left here we have a histogram that shows the gray shading is the number of great storms that occurred in spot groups of a given size. And so, so you can see that in the smallest spot group, there was 14 great storms. And during that period from 1932 to 2014, there were 71,730 spot groups in that range. And then you go on over. And so for the small bins, you could have, numerous, maybe tens of groups in that size. But by the time you get over to the 3,000 to 4,000 millions of hemisphere bin, those are all single days, because we have never seen 2,000-3,000 million spot groups on a given day. Now we go to the plot on the right. What we do there is we take the number of storms in each bin divided by the number of bottom, get the probability of a great storm for a spot group of this size. And you can see that as you get larger spot groups, the probability goes up, increases up to a certain point, and then it stops completely. And so we look closer at this 3,000, 4,000 bin, realize that all of the events there were between 3,000 and 3,500, and compare that with all days when we had spot groups greater than 3,500 millions of hemisphere on the sun. The number of events in both bins is similar, 71 on the top, 67 on the bottom, but the smaller groups produce all the storms, none for the ones that can go all the way up to 6,000. And Lee et al. Obtained a similar result for this. They used a different parameter. They used total unsigned flux. They were looking at flares instead of great magnetic storms, and their sample size was their period interval they looked at was more recent. But it appears that these large spot groups can, in a sense, become magnetically muscle bound with strong fields that overlie and suppress CMEs. One caveat here: suppression doesn't magically begin at 3,500 millions of a hemisphere. There's evidence for magnetic suppression for smaller groups, and we see larger groups that have storms, so they have CMEs, but just not at the 300 MeV level. So in conclusion, sorry for going a little bit long, extreme solar activity is a rapidly developing field with connection to research on active stars. I think it's important that the 774 SEP event has this huge size, 7 times greater than the 1956 GLE. To date, no confirmed sun-like stars have produced flares, but the sun may have done so in 774. And there's growing evidence for suppression of CMEs in large